Devine from Sandia. She's a principal member of technical staff. She's got a PhD in computer science from RPI, and she's going to talk about load balancing throughout her career. I assume your background has something to do with load balancing.
That's right.
I'll let you know we have 2 minutes.
Okay. So, thank you. I wanted to thank the organizers for inviting me to speak to you. It's really exciting to be here. My name is Devine. I'm from the Center for Computing Research at Sandia National Laboratories. And I'm going to talk today about load balancing throughout my career. And I'm going to start actually with the technical part of the talk about load balancing at HPC, and then also talk about how my career in HPC has really offered the opportunities for a lot of balance in other parts of my life. So in parallel computing, the idea is that we have many processors working together to solve a single problem. And so the first step in doing a parallel computation is distributing the work among the processors with the idea that, so let me back up. Let me say in this picture, what I'm showing you, say, a finite element simulation, and we might assign patches of elements to processors based on, as indicated in the colors. So each color of the finite element mesh is assigned to a different processor. And if we assume that for each triangle in the mesh, its solution values depend upon the solution values of all of its neighboring elements, then any place where the color changes, 2 processors have to talk to each other to exchange values. And if we're on a distributed machine, then that means they have to do some sort of message passing across the network in the computer. Or if even in a shared memory machine, they have to do some data movement up and down the memory hierarchy. So the idea in partitioning or load balancing, I use the 2 terms pretty much interchangeably, is that we want to assign the work to the processor so that the total execution time of the simulation is minimized. And here work can be whatever data we're using in our simulation. So if we're modeling networks of web links, then the work could be the websites. In a finite element simulation, it might be grid points or the elements of the mesh. If you're doing linear algebra, it might be matrix rows or matrix non-zeros, and so on. So I would contend that all of you have done some sort of load balancing in your life. You've probably all been on team projects in your schoolwork, and you know that the way to get the most efficiency in your team project is for everyone to have about the same amount of work to do, and for the work to be scheduled so that no one has to wait for other people to complete their work before he can continue making progress. You also probably know that the less time you spend talking to each other and in meetings discussing the work, the more productive you are. So that's the same thing we're going to do with partitioning. We want each of the processors to have an equal amount of work so that no processor is waiting idly for other processors to finish. And we want to reduce the communication between processors so that the computation can proceed as quickly as possible. So at exascale, or what makes a partition good? We want of course, to have balanced workloads. If we think about cases where even there's a slight imbalance in one processor, that's like wasting many other processors compared to having a balanced computation. We want good data locality because data movement is more expensive than computation these days. So partitions that have minimal communication cost either across the network or even within the node are really the best performing partitions. We also need our partitioning algorithms themselves to be scalable because they're often running side by side with the application. And we don't want the cost of partitioning to outweigh any gains we get by having a more balanced partition. The trick is that there's no single partitioner that's good for all applications. There are trade-offs for different applications. An application like the structural analysis shown on the left uses a single partition generated once. It uses it for the lifetime of the computation. So it can amortize the cost of the partitioning. It can use a more expensive, more careful partitioning because it can amortize that cost. On the right, I show a dynamic repartitioning scenario, where we have an adaptive mesh that's following a front from the bottom right corner up to the upper left corner. And the partitioning, or the assignment of work to processors, has to change as that front, as more elements are added or removed from the mesh. And so in that case, we're doing partitioning very frequently. We need something that runs very quickly and doesn't get in the way of doing the actual computation. For other applications, some of the trade-offs include geometric locality. What's most important is having things assigned to processors so that that are close together in physical space. Whereas in other cases, the data dependencies between items are more important. So imagine if I wanted to partition the people in this room to have discussion groups, a geometric algorithm might be good because it's easier to have a discussion group with the people you're sitting next to. But if you want to have conversations with your social network on Facebook, then we're more interested in the connections you have between people on Facebook, who your friends are, rather than your friends of your friends of your friends. Okay? So I'll talk about some of the different kinds of algorithms that we use in partitioning. I mentioned geometric algorithms where we partition based only on the geometric locality of the objects, assigning physically close objects to the same processor. So in the bottom left picture, I have an example of recursive coordinate bisection, which is by no means a new algorithm, but it's a very simple algorithm, very elegant. We basically take our domain, we put half the work on one side of the cut and half on the other, and then recurse on that until we get the same number of parts as processors. Here, communication costs between items are only controlled implicitly because they're controlled only by the assumption that things that are close together are the things that are going to communicate with each other. But this is a reasonable assumption for many applications. And these geometric methods have many advantages. They're really simple. I just explained to you how one of the most commonly used ones is written. And they're really fast and inexpensive, so we can use them for things like the adaptive mesh simulations that we showed before. Here I have an example where it's used in a chemical vapor deposition, where the mesh is following the surface that's being laid down in chemical vapor deposition. All the processors can really easily know the whole decomposition with geometric methods. If I keep track of what the cuts are as I'm doing that bisection, for example, I can know which regions of the domain are assigned to which processors. So if I need to do global search to see, say in a crash simulation, which surfaces are interacting with each other, which are now touching because of the crash, it's easy to do that global search with the geometric method. And for a particle-based simulation, like the cell simulation on the bottom right, we don't need any connectivity information for the geometric method. So particles which don't have connections like a mesh would have can be easily partitioned here. The disadvantages are that there's no explicit control of the communication costs. And so that leads to partitions that can have somewhat higher total communication volume compared to other methods. Another standard approach to partition is topology-based methods. These represent the computation as a weighted graph or a hypergraph, where the vertices are the objects to be partitioned. So if we were going to partition this finite element mesh, we would have one vertex for each element, perhaps. And then we would have edges between the elements that represent data dependencies, edges between the vertices that represent data dependencies between the elements. And we could weight the vertices or the edges to represent the amount of computation or communication involved. Then the idea is that we want to partition this graph so that parts have equal vertex weight, and the weight of the edges cut is minimized. So in this particular example, I've drawn it so that the edges that are cut or shared between two different parts have two different colors on each side of the edge, are the ones that will induce communication if I run this mesh in parallel. Does that make sense? So these topology-based methods have several advantages over the geometric methods. First, they're explicitly controlling the communication costs, so we can end up with a lower total communication volume in our partition. And they're applicable when geometric information is not available. So for example, in a network of a circuit, we don't necessarily have geometric information that's relevant to the circuit. And so instead, we can use the connectivity information in the circuit to do partitioning. However, these methods are significantly more expensive than geometric methods, and one does have to have topological information in order to use them, so they're more difficult to use for things like parking methods. Excuse me. Now, in my work at Sandia, I've spent many years working on a software package called the Zoltan Toolkit. Zoltan includes a suite of parallel partitioning algorithms, so all the algorithms run in parallel as a library with the application as it's running. And by having a suite of different algorithms that allows an application to experiment with different approaches and see what works best in his or her application. This is open source software distributed through Trilinos. It's written in C and C++, but it has a Fortran interface. And it's used in more than a dozen applications in Sandia as well as in industry and academia. So I have a couple of examples of some of the results and these are just a couple of recent results that we've seen at Sandia. By using a multi-criteria geometric partitioning algorithm in a multi-phase simulation, we were able to reduce the total execution time by a third. And this was a finite element simulation of an abnormal thermal environment. That's nerd speak for a fire that they didn't really want happening. We've also used it in social network computations where we were able to reduce matrix vector multiplication time of social network by up to 75%. And even more so if we then, instead of doing a row-based decomposition of the matrix, did a non-zero-based decomposition of the matrix, so that individual non-zeros were assigned to processors. So I think going forward, there are still technical challenges. We have more complex problems now to be looking at with vast amounts of data that's highly irregular, it's imprecise, it's incomplete, dare I say it's big. We have more complex architectures to work on with the many core systems and the GPUs and the deep memory hierarchies. And we have much larger computer systems. When I started working on Zoltan, we could easily get a paper published if we ran it on an amazing 1,024 processors. Nowadays, that's the starting point. And our algorithms need to be able to run on orders of hundreds of thousands of processors. We need to identify finer grained parallelism for applications, and we need our algorithms to be more scalable as well. Another problem or challenge in our area is software sustainability. There's a lot of legacy application software out there that still needs to be run. Weather codes, climate codes, engineering codes. And we need to help them run efficiently on these new platforms and provide some mechanism for performance portability. Is there a question?
Out of curiosity, how does this perform compared to the standard libraries that is widely used, such as Scotch and
So the question was, how does Zoltan perform relative to the libraries Scotch and Metis? Scotch and Metis are serial libraries. They have parallel versions. Parmenas comes from the University of Minnesota, and Scotch, PT Scotch, from the University of Bordeaux. In fact, Zoltan has interfaces to both of them. So if one's doing graph partitioning with Zoltan, it's possible that one's using Parmenas or Scotch underneath, or one could be using our native hypergraph partitioner underneath to be doing graph or hypergraph partitioning. So the performance is going to be much like Parmenas and Scotch if you're doing graph partitioning. If you're doing geometric partitioning, we use our own native algorithms for geometric partitioning. And just because the geometric partitioning has a much less rich model than graph partitioning, they run in order of magnitude faster.
Yeah, I have one more question. So, which one does perform better on discontinuous hierarchy and finite element methods or the partitioning?
Well, discontinuous Galerki methods still have a flux calculation between the elements, and so they would have a similar phase-space connectivity scheme. So the discontinuities are in the solution, not really in the graph of dependencies for the partition. Does that make sense? Okay. And we can talk about that one later, because I did PhD methods in my PhD dissertation. All right, so I don't want you to think that I spend all day sitting in an office writing and running load balancing algorithms. In fact, in my career, I think there's a lot of balance. I spend a lot of time working with application scientists at Sandia, and these are really meaningful collaborations to me because I like to see my software get used. I like to see results coming from it, see it in things like this fire simulation, plus the applications people generate really cool pictures for my talks, which is awesome. So those collaborations take a lot of my time during the day, but I really enjoy them. As a result of my software being used, I have to spend more time on software engineering than I might have to in a purely research position. So I was looking at interfaces, algorithmic design, testing infrastructures, things like that. I also, through the course of my career, I've had opportunities to do project leadership, and I spend a lot of my time working in teams, both within the labs and across the labs. So, for example, I'm part of the FastMath SciDac Institute, which is a collaboration among 4 of the labs and 3 universities. There's a lot of professional balance in my job as well. I have the opportunities to work on, to do service for the research community by serving on conference committees or holding leadership positions in professional societies. There's a lot of continuing education by going to conferences and workshops. I have opportunities to do mentoring, to help with STEM events, we had an interview event for middle school students to talk to women who are working in mathematics, and I use the term mathematics very broadly. You include computer science, engineering, even finance, and some of the business functions at Sandia. And finally, I find that there's a lot of personal balance in my job. I feel like I've had a really rewarding career over my 22 years at Sandia. I have very respectful peers, many of whom have become really true friends of me and my family. And I've done all this work while working part-time for the last 18 years. I have pictures here of my biggest experiment and most significant result for the last 18 years. All this has been while working part-time at Sandia, which I think has just been a fantastic opportunity. It's been really wonderful for my family. I can't brag on it enough. So the biggest challenge with working part-time is learning to say no when it's necessary to them. So I'll conclude by saying that I think load balancing is important, both technically and personally and professionally. And there are many opportunities at Sandia that I hope you'll consider. We have student internships. We have critical skills programs where Sandia will fund people to get their master's degrees. I think they have doctoral programs as well. And we host a lot of postdocs. So if you're interested in talking about opportunities at Sandia, I'd be happy to talk.
Thanks. Okay, so since the first